So hello guys, welcome back, and here we are with the problem that I'm going to tell you today. And this problem caused a bit of confusion among the students and the faculties. So let's see how we can handle it and understand it together. So the problem is the following: that it's a sequence problem, which is the following: that if summation of so n is a serial sequence, the problem says that if summation of modulus of an minus 1, the consecutive difference, this is convergent, then what can you say about an? So an, you have to prove an to be convergent. So this is the actual problem. Okay, so now there are two lines of proof, and the two lines of proof, one line of proof is really easy and it's easy to understand. But the other line of proof that was along the line of Cauchy sequence. So as a prerequisite to this problem, what I will do is that I will explain to you the ideas of Cauchy sequence. So what is the Cauchy sequence? So Cauchy sequence was actually there, it was defined to prove convergence without having the limit, because in the usual limit definition we need the definition of convergence, right? So now in this Cauchy sequence, it doesn't need the require the definition of convergence. So therefore, what is the Cauchy sequence? It tells you that if an is a sequence, real sequence, and if modulus of an minus am, that is in some sense the difference, is less than epsilon. The sequence ka difference is less than epsilon for all m and n greater than or equal to certain n. If there exists such a, for all epsilon, like if you fix epsilon for all epsilon greater than 0, okay, there exists such a n, the capital N, such that for all m and n greater than or equal to that capital N, an minus am is less than epsilon. In some sense, the difference between the an and am are decreasing. Okay, that is, it's going towards 0. So this is what Cauchy sequence is trying to, you know, like enforce into the idea of convergence. So let's focus on this problem. So one way of doing is that if you observe, it's telling that summation of the consecutive difference of sequence is convergent, then an is convergent. Now the basic idea is the following. So there are two lines of proof. One line of proof is that it's very easy. One line of proof that is correct is if summation of modulus of an minus 1, this goes is convergent. We know that if a sequence is convergent, then the sequence also goes to 0. That is an minus 1. This must go to 0. Okay, this implies that. Okay, and but this proof is not correct. I'm sharing it again. So this means that an minus 1 is less than epsilon. If you fix epsilon greater than 0, then an minus 1 is less than epsilon for all n greater than or equal to certain n. So to use the property of Cauchy sequence, what you can do is that you do am minus an. You can use triangle inequality now. Let's say n is greater than m. So you write an minus am minus a plus an minus 1 minus an minus 2 plus dot 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 an minus am plus 1 minus am. You can do this. And how many such sequences are there? Number of sequences that are there is the following. It's am plus 1, then got the an minus 1. So it's around, I think all of them have, uh, I think m minus n plus 1. I may do a small error, I think. Just give me a minute. If it's a4 minus a2, then we do a4 minus a3 plus a3 minus, so it's n minus m. Okay, so now observe that if you take this corresponding n, this capital N that you have got over here, so if you take that, you get that am minus an is less than, if you take this greater than n, then you take that am minus n is less than m minus n times all of them are less than epsilon, right? By this property, since we have assumed that this is happening into less than into epsilon. So, but observe that this proof will not work. Why? This proof will not work because in Cauchy sequence you have to find a single epsilon. Okay, but here this proof will not work because this n minus n is, it is varying. Okay, it's not a fixed constant. You can take, if you take m to be 1000 n, so it will be 999 n, so it can change a lot. So therefore m and n, so therefore this is not a constant but this is a variable. So this line of proof, that from this you cannot tell that it's a Cauchy sequence. Okay, this error has been made by some of the students, so this is to make yourself very clear. So let's go to, this is a possible proof but this is not a proof. Okay, why this is not a proof? Because understand, in this we are assuming just the property that in the consecutive difference going to zero. We are assuming just this property. Okay, that's why it's not happening. We are not like, this is a much more stronger condition. Okay, this is like a corollary of that. So we need much more stronger conditions of than this to prove this. So therefore the just the condition, in this proof we are not using that this is convergent. We are just using the fact that the consecutive difference is going to zero. So that's why this proof is not working. Okay, so now we will do another proof, that is the actual, like one of the proofs, not the actual proof I should say. The proof is this. It's very simple. If summation of modulus of an minus 1, this is convergent, this is absolutely convergent, you can say. So therefore by the idea of absolutely convergent implies conditional convergent, summation of an minus 1 is also convergent, right? Why? Because absolute convergence imply conditional convergence, right? So therefore if you now observe this, this is nothing but, this is very simple. If you add it up, it's an minus 1 plus an minus 1 minus an minus 2 karte karte plus a2 minus a1. If you see, all this will be cancelled one upon another and you will be left with an minus a1. Now this is convergent, so an minus a1, this sequence is convergent. Okay, and therefore it implies that an is convergent. It's very simple. Okay, so we are getting that from absolute convergence, we are getting that it's conditionally convergent, and then we are getting that an is convergent. So this is the proof. But there are certain issues, there are certain like the counter example what I'm going to share with you is the following. So understand the way of proof. So the condition is that this is required to be convergent. So one way the proof, the wrong stuff was this, that this implies that this goes to zero, and it was one way of proof which proves that an is convergent. So therefore in this proof we have only used this to this result only, and therefore this result is not sufficient. We have shown that it's not convergent. So what is the counterexample for that? The counterexample for that is, if you take n to be 1 by k from 1 to n. So observe that an minus 1 is nothing but 1 by n, which goes to 0, and an is also a harmonic series, so it's not convergent, it goes to infinity. So you can understand that this condition will not alone suffice that an is convergent. We need some more stronger assumptions on this. Now if we assume this already an is convergent, we cannot give a counter example. But what we can say is that to prove that this implies this condition is not sufficient. Okay, this condition is not sufficient. We need some more extra conditions that are sufficient. Okay, so this is the basic idea. This is a basic idea, and there's some confusion regarding this, so I was helping. I made this video to make the confusion clear, and I hope you enjoyed the video. If you have any other questions, do let me know. We can add some more, by part 2 sequence of it. All the best, guys, and I will see you in the next video. Stay tuned and stay blessed.